expect, and I hope you all enjoy it.
Thanks, Christoph. So welcome, everybody. I'm Rob Lindeman, and I'm going to talk to you today about some work that I've been doing, for about 20 years now on virtual reality, and kind of take you on a little bit of a research journey on where things are, where I think things are going, and some of the focus that I have. So the talk is called Pushing Virtual Reality. So the idea is we've really been doing virtual reality for a long time, but it hasn't really taken off. And so a lot of my focus has been on why this is and how we can make virtual reality more effective, more useful outside of laboratories where it's been most of the time. And so yeah, I'll show you kind of my take on where we've come from and what we've been doing to make this happen. I want to say a little bit about the university that I come from. So Worcester Polytechnic Institute is pronounced Worcester. If you've ever been to Boston, they have a very strong accent in Massachusetts, so it's Worcester. It's about 40 miles west of Boston. As I like to say, we are a three-letter engineering school in Massachusetts, which there's another kind of famous one closer to Boston. We're also voted the snowiest city in America. In February, we had this much snow on the ground, which is always a lot of fun. It's a traditional engineering school was founded in 1865, so this year is our 150th anniversary. We have about 4,000 undergraduate students, 2,000 graduate students, about 240 faculty members. And it's been founded on this notion of theory and practice. So we really try and produce students who have a very solid basic foundation in whatever it is they're studying, but also have the ability to apply it to provide impact to the world somehow. So it's a very practical type of place. We really want people to roll up their sleeves and get stuff done. So how I got into VR, so I was born in 1965. It's kind of I think, a really interesting time to be born. I was always into science fiction. I wasn't the best student in grade school. I studied computer science in college, took a course when I was in high school, studied in computer science, and I've always been kind of an optimistic person. And as an adult, I took a kind of a normal computer science job after I graduated. I moved to Germany. I worked there at a software company. We were doing factory automation software, and I ended up doing a lot of user interface design for the systems that we were building, which is how I got into user interface. And I went back to the States and got a PhD, and has led to really kind of the best job in the world, which is kind of another talk, but that's okay. It allows me to really follow my passion, which I think is what I try and instill in the students, is to really follow something that you're really interested in and to have a plan to get there. So the motivation for me, I did a lot of reading. So I read a lot of the Neuromancer series and kind of visions of the future of virtual reality. And the talk was always, it's kind of unfortunately always a little dystopian, but the thought was that virtual reality is something that is going to change the way we do just about everything. It's going to change the way we learn and change the way we interact, the way we shop. And so I actually took a lot of vision from these early works. And then there's some kind of later things. This maybe some of you remember this movie, Westworld, which was kind of a virtual world. It was, you could go on holiday to a Western town or to a Greek town, and they were robots instead of virtual characters, but it was the same idea. You could go and interact with them and kind of go on an escape kind of holiday. So this kind of got me very excited about the whole concept. Now, is this something new? So other people obviously have had similar visions to this. Morten Heilig developed a system called Sensorama. They didn't make very many of them, but the idea is it has a multisensory experience. This was mainly a motorcycle ride, and they had 3D, wide vision, motion, color. Wow. They had aromas and wind built into this. The seat would vibrate when you sat on it, so you'd feel kind of the motorcycle ride. And so this was kind of a vision of how could we bring somebody into a virtual world. So it's not new, and it seems to be something that we've been chasing for a while. The interesting part is where we are today. So if you think about the state of things, in the 80s and 90s, there was a lot of hype, a lot of excitement about virtual reality. It was just around the corner, and it was going to impact a lot of things. But it didn't really make any inroads in everyday life. So the technology was lagging. Things were still a bit clunky. There was a lack of understanding kind of the usability issues of things. There was a lack of the virtual reality community is always looking for a killer app of some kind. And so VR really kind of stayed in mostly in research labs. There were some success stories. So in surgical simulation, military training, there's been some good work in phobia therapy. Oil and gas is very interested in visualization. In Germany, the automotive industry has embraced it as a way of doing less expensive design for new motor vehicles. But in terms of everyday life, it hasn't really made inroads. So we've moved to the 2000s. Video games really start to take off here. So consoles get very powerful, PCs get very powerful. Hardware is now allows us to do things that we couldn't do before. Programmable GPUs, graphics processing units. Costs come down. And a lot of interesting new interface devices come. The other thing is the understanding of the 3D user interaction, so how people actually get work done in these spaces, grows a lot, mainly because of high-quality technical conferences and journals that come up, where there's a growing pool of researchers who are working and kind of confronting these issues. So IEEE has had a series of conferences. ACM has had a series of conferences that have really gone and explored a lot of these things, where we used to have 1 or 2 conferences on user interfaces and 1 or 2 journals on user interfaces. We now have a lot more targeted types of conferences, such as tabletop interaction and mobile interaction techniques and so on. And so we now have a much deeper research literature to go to. And not have to keep reinventing things, or we can learn a lot more from each other. The other thing is gaming has really emerged as the killer app. So especially in the current round, which we'll talk about in a minute, gaming is really kind of a driving force behind a lot of what's happened in many, many types of interactive graphics techniques. So my long-term goals are really to make virtual reality more usable and, of course, do cool stuff. I think it's really important to do interesting, compelling things to keep people interested, have students come and want to work with you and kind of push the boundaries of these things. So in the 2010s, we've seen just an explosion of new interface devices and other types of devices. So the Wii Motion Plus came out and really kind of changed a lot of how we do gaming. Now you could stand up and you could play tennis. So it really kind of changed something. The Kinect came out and people were now kind of using their whole body to interact with things. Mobile devices came out, and now you could do so many things walking around. You weren't tied to a desk anymore. So it's a lot of kind of multi-person interaction you could do. And then the number of virtual reality headsets, where we used to have 1 or 2 companies that would come out and deliver their headsets and then go under because the 200 research labs in the world would buy them and nobody else would, and so there was no business model to keep them in business. Augmented reality headsets, so I don't need to preach that to this group, but the number of devices and the companies that are investing in these devices, there's a lot more money right now being put and focus being put on these devices. There are lots of different types of new controllers, hardware mashups, so people putting different types of hardware together that they weren't thinking before, and many, many game companies now are really picking up on this a lot. So if we look at this, so this chart shows virtual reality. So it's kind of the virtuality continuum here. So a real environment, augmented reality, augmented virtuality, and virtual reality. And you can kind of see these are the devices that are currently available. So headsets currently available for the VR space. These are the ones that are 3 months out and 6 months out. So this kind of gives you a showing of the types of technologies that are emerging. Another one is this graph. And this shows just head-mounted displays, and the closer you are to the bullseye center, the closer you are to releasing a product. And so what this shows is divided into two sectors. One is a head-mounted display that has the display integrated into it. And then this other one, which is really interesting, are head-mounted displays that you take your phone and you put your phone in, and that becomes the brains of your device. And the optics and everything are in another piece. But if you think about a game-changing device, this has changed. We don't carry watches anymore. We don't carry cameras anymore. We don't carry video recorders anymore. This is, again, another kind of example of how this technology, because it's mass-produced and it's cheap, can be used and leveraged here. And you see that there's just a convergence, a lot of devices that are coming to market. And this one shows other types of controllers. So this is kind of a sensing devices that sense your body movement either through a device or through vision. And these are kind of controllers that allow you to move. So the Virtuix Omni is kind of a walk-in-place type of device. So there are a lot of kind of an ecosystem here developing of different devices that are coming to market, which is important for further work. So if we think about virtual reality, this is in your dissertation, everybody needs to define their terms well. This is kind of the definition I came up with for my dissertation, which is virtual reality is fooling the senses into believing they're experiencing something that they're not actually experiencing. So you're fooling the person somehow into thinking that they're someplace else, or that they're feeling heat, or that there's a monster after them, something. But it's really about fooling the senses. And I've kind of updated this a bit, which is a good thing over time. But in general, this still holds. And other people have used this. Jim Foley used it in his keynote address. He kind of asked everybody, give me your definitions of virtual reality. And in 2009, he used this definition in his keynote address at the IEEE Virtual Reality Conference, because he said it kind of captures things. So there's some validity there. So virtual reality systems consist of many, many parts. And this is really important to see that there's really a lot of things that we need to do well in order to deliver a good experience. So obviously there are users in the system, there's content, so what are we trying to have the users do, or what do they see? And we need some sort of rendering, we need graphical rendering, and audio rendering, and touch rendering, and smell rendering, and things that we need to add to the system. We have to track things, which is another kind of really big problem, which overlaps a lot with augmented reality. There's physics, collision detection, so knowing when things hit each other or near each other. Then there are interaction techniques. How do I select, if I want to select you, how do I do that? If I want to do this, and I shoot a ray from here, how do I decide if it's you, or you? Kind of these things that we kind of take for granted in the real world by kind of moving around. How do I do these kinds of things? And then typically there's some sort of networking involved, autonomous agents. There's a lot of computer science behind a lot of this that we're looking at, but it goes beyond also. For me, the really important thing is this user. So the user is the whole system doesn't exist for the system's sake. It exists for the user. And so for me, this interaction, this intersection between the system, the most important thing is to look at the user. And because in the end, it's about the perception, the cognition, and things that the user has that's most important. And the keys are obviously fast everything, rich everything. So you want very high fidelity, realistic rendering that you can get. You want very low latency on all the things that could break the system. You want ease of use, both for the users, but also for the programmers and the content creators, so that you can get interesting content into the game or into the environment. You need designers to understand how do I design this in order to make sure that it's compelling for somebody. You don't want programmers making your artwork, which is what we've done a lot in virtual reality, is we just make nice cubes or spheres because that's what we know how to do. What you really want to do is work with artists and people who know the human form and motion and these sorts of things. And then this notion of responsive expressiveness. As a user, I want to be able to tell the system what my intention and have it respond to me. And then we have this dialogue that happens in order to make it. So if we think about reality, what is real reality? So the great philosopher Qui-Gon Jinn has said, given us some really wise words here, that your focus really determines your reality. So what I present to you and what you're focusing on really helps you understand where you are and what you're currently doing. So the translation here is really that reality is just an illusion. So you really should try and fake it, which sounds really kind of strange. But in computer graphics, it's always said if it looks good enough, it is good enough. So for some researchers, physical correctness doesn't matter. It matters that if it looks good enough, if it looks believable to the person, then it's good enough. So what about cost? So back in the day when I was working on my PhD, I had one of these devices, which was about this large, and had 4 processors and some amazing processing. And now I have, this device which costs $500 as opposed to $250,000, which does way, 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 way more than this device could ever do, and it does all the physics processing too. So actually, they've offloaded a bunch of things onto this device. So now the cost has come way down, and this is all driven by the game industry. So the only thing that has made this cheap is volume, right? So you can just sell heaps and heaps of these. So the other thing is head-mounted displays. So back in the day, you had this $80,000 dual CRT display that you wore on your head, which was really dangerous because you had these big electromagnets next to your brain. And now we have wide field of view, low latency, consumer-grade devices that are emerging, and this is only one of them. But there are several now that are coming up that are making this a total commodity item, which is a big shift. So my lab really focuses on this notion of multisensory cues. So I'm really interested in all the senses working together. And the idea is, if life is a multimodal experience, the virtual experience should also be multimodal. So I should have not just good visuals and sound, but I should have some touch, I should have some heat, I should have pain maybe, if that's what my experience is about. And I should really try and feed the person as rich of an experience as I can, and not limit it to what the technology can currently provide. So think about the user and the user experience. And it might not be providing exactly the same experience, but the essence of what the experience is trying to convey should be incorporated in the stimulation I provide. Okay? So the idea is that the sum is going to be greater than the parts. So you can balance some things out. For instance, if you have limited field of view on your visuals, you could use spatialized audio to alert the person that there's something over here, and then they can look over there. So if I have this limited visual field of view, I can combine these modalities together and compensate for maybe some limitations in some of the technologies. You just need to understand them really well. So in the senses, I mainly look at all of these, but see, hear, smell, touch, taste is kind of the types of things. And I would argue that visuals we do very well now. Audio we do very well. Smell is very hard, but there's some work being done on smell. Touch we also do pretty well in certain scenarios, and I'm gonna touch on some of these. And taste is still way out there, so I'm sure the Japanese will come up with a great solution to the taste problem. The Japanese do what the Japanese do. So some work that we did a while ago now is to develop this Tacavest. This was developed when I was working at a research lab in Japan at ATR. And the idea here is to develop a wearable system with a bunch of vibro-tactile points that are built into the vest. And so this has 16 points of contact. And this is the system actually built into the Naval Research Lab funded us to develop this system. What they have is this is not a soldier, but this would be a soldier wearing a head-mounted display. They have a full flak jacket on with a full pack, and they run in place. They have a weapon that's being tracked. You can see the markers in the head. So they're running through this in a building clearing exercise. They're running and they're kneeling, they're laying down, and they're aiming and clearing a building. But they have no sense of touch when they're walking around. So if they bump into something, their avatar is going to stop, so their view movement will stop, but they won't actually know why they stopped. And what we do is we translate this bumping into something into a vibration that they feel. Or if they back into something, they'll feel that they backed into something because they get the sense of touch, right? And it's not a perfect cue, but it's enough for them to understand. And it really solved the problem that they had, which was this lack of sense of touch because of this limited field of view of the headset. So I'll show you a little video of this.
Right now on Daily Planet, introducing touch to the virtual world. The Tacavest lets you feel everything you can see in a simulated environment.
Plus, looking good, sounding better. We'll show you the best way to engineer a building to make the acoustics crystal clear.
And NASA's newest workhorse, the Lemur robot. It's designed to keep the International Space Station.
As we go about our daily lives, all our senses combine to inform our reality. And on our computers, sight and sound combine to create convincing virtual worlds. Now at WPI, the Worcester Polytechnic Institute, Dr. Robert Lindeman has another piece for the puzzle. His so-called Tacavest adds the sense of touch to our virtual repertoire.
It's very immersive. Until you really experience it yourself, there's nothing quite like it. It really is like being in the space. You can still see in peripheral vision, you can still see the outside world. But really, since what's dead ahead of you is the game, it really refocuses your sight. And you really have to adjust to it. It's very, very immersive.
So the Tacavest is actually made up of a number of pieces. Because humans come in different shapes and sizes, what we've done is constructed the vest so that it's adjustable.
What Eric's wearing is simple yet ingenious. 16 standard pager motors are wired together, attached to neoprene. The pieces of neoprene fit together to form an adjustable vest, ensuring that all the motors remain in contact with Eric's body. In traditional video games, if you run into something, you might hear a thud. But if you're wearing the Tacavest, you'll feel the impact. And if you just brush against a wall, you'll feel that differently.
What we want to be able to do is to have Eric be able to interact with a keyboard. And it hooks onto a holster.
So that last bit there of this keyboard, the way, so anyway, it's kind of a marketing piece. There's a lot of hype involved. But this last bit with putting a keyboard here, so the idea is we mounted a keyboard here, and he uses the traditional keys that you use in a first-person game, what's called the WASD keys, to move around. But he has his hand in a comfortable place. This was kind of a breakthrough in my thinking, because oftentimes in virtual reality, you see people doing this and they're waving, you see Minority Report, you see these people doing stuff and they always have their hands up. You can't do this for a long period. We just don't want to do this for a long period of time. Same thing with the Wiimote. When the Wii came out, everybody's up there playing tennis. And after 2 weeks, people are like, I can sit on the couch and do this, and it's kind of the same result. So this notion of people getting up and doing stuff is great for a while, but over long periods, it's just not tenable. You need something else. And so the fact that they could keep their hand here in a very comfortable position and work the keys was kind of a big deal, because you could do this forever as opposed to keeping your hands up. And so that actually kind of fed my later research. We then built this thing called a Tacticage, where we put Anakin, the mannequin, inside, and he would wear this, so the user would wear this Tacavest that we developed. We then added fans around it, so that now we had wind that we could introduce into the system, which is also part of the sense of touch, so that when they saw the grass blowing or they saw the leaves blowing, they would actually feel physical wind from the direction. These were all under computer control. They could feel the wind from the direction that the wind would be coming from. And we're exploring this actually really deeply right now. In addition, we have motion tracking cameras that are tracking the fullness before the Kinect, tracking full body motion of the user, so we can take that into consideration when we're driving the system. And this is all developed in-house. These are all the control boxes here, using standard software engineering. It's all socket-based, so it's all very vanilla kind of designed. And the cage allowed us to do a number of interesting things. We now had laptops that were powerful enough so we could make the whole thing completely wireless. So you wear a backpack with a gaming laptop, you connect the head-mounted display to it. You had wearable Tacavest, which ran on batteries, so it was also wireless. We had the fans. We talked wirelessly to the fans, so we could do that. Again, with no cable. And then we had a number of different types of interaction techniques. We had this hip-mounted keypad. We also had a surfboard interface, or a tilt chair, which I'll show you in a minute. And we had this very inexpensive prop that they had as a weapon. So we had a wireless mouse with just a tube. And they would use this as they moved around in the environment in a first-person game, and they could shoot it. And it was just this little piece of tubing here had a huge impact on a sense of presence, because they felt like they were holding a weapon as opposed to clicking a mouse or something. And this we demoed at the IEEE Virtual Reality. I chaired the IEEE Virtual Reality Conference and brought everybody over to WPI for a big demo night. And so this is that. What we did subsequent to this is to look at other ways of travel in virtual reality. So you think this is a keypad that allows me to move forward, back, and I can strafe left and right. What we wanted to do is to see if we can use something like a Wii Fit balance board, which is a sensor board that you stand on and allow you to kind of surf on it or snowboard on it. So you stand sideways on it, and you kind of put your arms up like this, and you can control your movement using this sort of stance. So we wanted to see how performance compared using a tilting board versus a non-tilting board. So the Wii Fit balance board doesn't actually tilt, at least not perceptibly. And so which actually jars the brain, because the brain expects if you lean forward on a board, your vestibular system will change based on how you're tilting, right? And so we wanted to see if this had any effect. And so we ran a user study, and one of my students did his master's thesis on this, on looking at how you would compare a tilting versus a non-tilting travel interface for virtual reality. And so this shows calibrating the system. So he's standing on a Wii Fit balance board, which is on top of a physically tilting Reebok sports board, which we found. But we've put blocks underneath so it doesn't actually tilt. Okay? And so this was calibration where what he does is he stands on the board, and when he wants he built this environment in Unity, and he flies around. There are these power canisters that he has to fly through. Basically, it's just fly around and pick up these canisters as you go. And the speed is controlled by your arm lift. So the higher you lift your arm, the faster you're going to go. So you control your yaw and your pitch based on the board. And you control your speed based on how you lift your arm. So he went through, he ran a bunch of subjects on this. And then he goes through, takes out the pieces of wood. Sorry, let's skip ahead. And then, and now he's on the board. And now he's calibrating, but now you see the board is actually tilting. So this is actually, it's a very small change. All we've done is remove this. And now, so it's the same environment. He goes in, he flies around, picks up the canisters. He did, anyway, I won't go deeply into the study, but he did a very controlled study on just up and down movement versus side to side movement, and then kind of free movement. The interesting thing is that he found that there was no difference in performance, but people got noticeably sicker if you did not let them actually tilt, right? Which is a really weird thing. We weren't even looking at this, right? We were really just trying to see performance-wise, does it make a difference? There was no difference, but many, many, many subjects dropped out because they were feeling sick, because the board was not tilting. And the Wii Balance board doesn't tilt. So it's designed for a certain thing. It actually does that poorly if you're in a first-person view. And it's because the brain is not receiving the signals which is why people get sick in VR anyways, because of latency, and the brain is not receiving the signals. So that was an interesting finding. I'll skip this. We've done some smell research, but I'll skip that for now. We haven't gone too deeply in that. We could also apply the same type of multisensory approach to teleoperated robotics. So if you think about an operator of a robot, there's a lot of understanding that an operator needs to have of a remote environment that has very limited sensors on it, right? It might have a camera, it might have some proximity sensors, some motion sensors, heat sensors, and all this data is coming back to an operator who has to take this, somehow fuse it together and make actionable decisions about how I'm going to move the robot or how I'm going to move the robotic arm. And it's a lot of mental gymnastics to figure out, what should I do? Sometimes pulling back on the stick leads to the robot arm going down just because of the current pose of the robot. Or if I turn this way, if it's a mobile robot, then I need to understand what that's going to do because I don't want to break the robot or fall off a cliff or something else, get stuck. And so I have a PhD student who looked at this notion of applying multisensory feedback to teleoperation as well as virtual reality. And there's a lot of similar problems here. You have limited sensing and so on. And so the goal was to try and have the operator make better actionable decisions, lower the cognitive load. The more time an operator spends understanding where the robot is, the less time they have to spend actually looking for victims, for example, or trying to do something else, because they're spending these cycles on, wait, so what do I have to do, rather than missing somebody who's laying injured somewhere. So this was really spurred on by Fukushima and this work. So the traditional kind of leading interfaces at the time have the following elements. So this is the robot, and then these are sensors that are sensor data that's coming back from the remote site. There's a camera feed. There's a map. It looks a lot like a gaming interface if you think about it. And the map is being generated on the fly as the robot moves around the space. There could be a rear-facing camera, so this is kind of a rear-view mirror of some kind. So this is one example. Here's another one, very similar. Here's the robot. Here's the camera feed, and this is the generated map. Instead of it being a separate map, they actually have it. They show you the boundaries that are being processed. Here's a map layout, and then there's a bunch of interface widgets that you can click on. And so what my student did is he took the same technologies that we use for the vest and made an 8-direction belt that you could control the vibration points around the belly of the operator. So for example, if the robot had a bunch of sensors around it and there was motion over here, the operator would feel a tickle on the side. And the way this used to be displayed was with a little color that would change on a certain place on the screen, or maybe a sound being played. And so what he wanted to do is to see if we could offload this from the visual sense, which is really taxed a lot, to something else to free up the visual sense for other things, because there's so much, we have so much bandwidth through all of our senses, and so much is being done through visuals. Can we make this better? And so his experiment, again, rigorous experiment, he set up a ring of, this is the robot, and this is the environment that's being, kind of the walls that are around the robot that's being generated from the sensors on the robot. And this ring here represents proximity feedback to objects in the environment. So the robot's here, there's a wall over here, so you see these three are very hot, right? And this one's very hot because of this, the proximity to this one here. In addition, the operator is feeling vibration at those points as well to show proximity to things around it. Okay, and there's some other elements here. Another important element is what was really kind of revolutionary in the HRI world is typically in the previous examples, the view was fixed. So the view coming from the camera was fixed. And what we introduced is a way for you to pan, as the physical camera on the robot moved, the panel in the display would also move, as opposed, so that because the robot could be facing this way and the camera's facing that way, and the operator, again, has to figure out what the pose is. This is one of the problems. And so, let me go to the right place. So this kind of shows the interface. He ran a set of studies in a simulated environment. This is the robot. This is, again, these are being generated. You can see the proximity sensors firing. And again, it's really tough to show this in a presentation, but the belt is also vibrating with the intensity of, depending on how red the elements are. The goal here was for the operator to go and find 16 red balls that are hidden somewhere in a debris-filled room. So they had to navigate through the room, and these were supposed to signify victims. So they were going into a collapsed environment and try and find victims in the scene. And what he found is that the vibrotactile feedback helped, that the subjects took less time. They were more thorough, but there was also some confusion about if a lot of stuff is vibrating at the same time, there's a lot of confusion about that. And so we did a further study to figure out whether varying the intensity versus varying the frequency of a pulse. So instead of just, it would go, that was better than actually just changing the, is that clear? Okay. So we think about the real world. We have these fast update rates. Like here, the rendering is really good, right? We have really good physics. Like I can pick stuff up and drop it, and it just kind of works. I have nearly infinite fidelity. So the range of the visuals here is amazing. I have massive numbers of objects, all these players, and there's really no lag. And this is kind of the goal of what a lot of VR is, to try and reproduce this type of thing. It's really hard, right, if you think about it. And computation's getting closer, and there's, again, if it seems good enough, it probably is. We think about the virtual world, so where are we on this? So it's a lot, right? You're asking a lot to try and reproduce reality. So we have virtual actors, which are, in some cases, really indistinguishable from real actors. So we see this in movies and games now. We can do this at interactive rates. And we have virtual crowds that show emergent behavior, so things we haven't programmed in. We have interface devices that allow us to act more naturally. We have content, this is really important, we have content creation tools that allow anybody who wants to develop content for these things. It's really, really important. This is crowdsourcing. This is allowing the public to generate stuff, which is really important. So if we look at this example, so this is a military example. I apologize if people are not game about the military, but this is a military type of application that shows kind of the cutting edge of stuff that we can do now. If you look at a lot of the scenes, there's some very subtle pieces that they've put in. The movements are kind of jittery. This one is actually kind of funny, but this kind of shows the pose that you can put this guy in. See a little butterfly come and go, and some of this is, trying to develop new camouflage, or so this is kind of one. This isn't even like a high commercial success game, but it kind of shows you that things are pretty good in some cases. If you think about the visuals, we're doing pretty well. The typical user interaction Bible work talks about kind of breaking down user interaction into smaller parts. You think about things that you would do at a very low level. I need to select an object. I want to pick up that cup. I want to pick up the cup. I want to manipulate it somehow, drink from it. I want to put it back down. Navigation. How do I know where I am and where I'm trying to go in the space, right? This is what we do in the real world. Oh, I'm here. Oh, here's a map. I want to go there. I know where I am. How do I do that in a virtual? People get lost a lot in virtual reality. And so there's a lot of work on this notion of wayfinding. And then there's, okay, I know where I want to go. How do I get there? Do I walk in place? Do I use a keyboard? Do I point and fly? Do I surf? Right? This is kind of a different problem, but a really interesting problem to look at. And then system control is, how do I load a file? How do I kind of interact with the system? Symbolic input, if I want to annotate something or want to speak. And then avatar control is a relatively new one, is kind of how do I control myself? Am I using some sort of motion capture thing that allow, if you and I are in the environment, I can move around and you'll see my movement somehow, and how does that, how do I do that? So there's actually a lot of conceptual films. If you haven't seen, these two are really interesting. So go Google World Builder and Site and look at these concept videos. They're actually really interesting and very inspirational in terms of how you could make, for instance, how you build a world from within the world itself. So if I wanted to build this door and I'm standing here, I could kind of get my tools to do it. In the virtual world, I also have tools that I could use to do that. And typically what's done today is somebody outside the world has a desktop and they say, oh yeah, here I'm going to use my mouse or my tablet, I'm going to create this, and then okay, I'm loading it into the world now, and then they load it into the world, and then it shows up in the world. And that process is kind of disjoint because there's a back and forth, oh, the door's too big, or it's the wrong color. And if I could do it in the world, maybe I have a better sense of how it's going to look or how it's going to act, because I have just a better perspective. And so there's some work on this. Iron Man, if you watch the Iron Man movies, the interfaces are really, really made up. Really interesting, right? So how could we do this? So when you watch these types as a researcher, everything is kind of ruined for me, because when I watch them, I try and figure out how would you actually do that in the real world. So now what? So we have head-mounted visuals, the Oculus Rift, Sony Morpheus, there's a bunch of HoloLens coming out. I honestly think we're kind of done with head-mounted visuals, which again, some of this is controversial, but that's okay. Spatialized audio, we do audio actually really well right now. Tracking the user, well, there's a couple things we need to do. We need to track the body of the user, and we have some really good technologies for that. We have to maybe track the fingers, which is a little bit kind of finer grain. We have some good technologies to do that. So we're kind of, I would say, almost done in that sense. In terms of the technology, we just need to leverage it at this point. We need to be able to scan the environment. If we want to be able to use things in the environment, like where is this physical cup, I need to know where it is. I need to scan the environment and know that if I reach my hand out to pick up the physical thing, where it is. There's lots of technologies now for doing this. And then there's a lot of crowdsourced things. If I want to do something on a larger scale, I have photo libraries that allow me to do that. I have GPS data. There's a lot of information now, security cameras, that I can use to generate both the near field as well as the far field, or the larger area. So this is not nearly done, but it's almost nearly done. Touching the environment is kind of hard. If I'm doing surgical simulation and I have, let's say, an arm that pushes back on a scalpel-like thing that I hold in my hand, for that particular, or I'm doing laparoscopic surgery, I have solutions for those today. They've been around for a decade. But if I want to, walk up and feel the wall and feel this and have everything kind of, my arm is going to stop when I move, that stuff the general solution we don't have yet, right? So it's still, but for many applications, it's okay. User interaction is still a big problem, which is kind of what I'm looking at. So I've been looking a lot at things beyond visuals and sound. So one of them is the Tacavest system that we've come up with. And this, again, I showed you an early example. Some of the problems with fans, this is really mundane. Some of the problems with fans is it takes a while for them to start up. So you apply voltage and they start spinning. At some point you feel wind. If I want to stop it, I have the same problem. I can't just stop it. Well, you could, but not easily. And so one of the things that we wanted to do, and then a person is moving around, we want to be able to blow on them wherever they're moving, because they could be moving around in the space. And so what we did is we took fans and we put them on pan-tilt platforms, so standard pan-tilt camera platforms, and we control them by the computer. So when we want to blow on it, we always keep them blowing, and when we want to blow on a person, we just look at them like that. When we turn it off, we just point it away. So it's always spinning. We can quickly make them feel the wind and not feel the wind in this way. And I'll show you a video.
Okay, so now we're going to see a little. And this one comes in. Brilliant. Yeah, bravo.
Oh, the number 5 kicked up too. This guy kicked off too. How's him?
Right, which one?
This one, when you got close.
The shotgun.
Okay, so if I go to the other side, will these follow me? No. Okay, well, we can have to wait a moment. Right, yeah. That's it.
For emergency situations. So they have a very elaborate, detailed model. They have all the visuals. They have all the sound. But what they don't have is the actual feeling of you're out on this rig and something's happening. So what they want to do is add wind to that. The other thing is a lot of the machines they have they vibrate the ground a lot. So they turn on a big generator and so they have a lot of these big devices, and they wanted those to vibrate the floor. So they also had us build a system where we took they're called butt kickers, these big low frequency actuators, and we put them around the floor, and again, put them under computer control, and we can now control the vibration.
Hard to see.
It really is looking beyond what you would typically think, because again, I think we do a lot of the things. So we think about, sorry about this thing here, improving interaction. So the virtual world is really not like, it's not Volkswagen, VW. So the virtual world is really not like the real world. And this is kind of an important thing. If we think, we may think this is what we want, but getting there really requires to be really creative with solutions. So we need to create user interfaces that are easy to learn and use, expressive, and scalable for different types of things. And as important is non-fatiguing. So we want people to stay in for a long period of time so they can use these to get real work done. So one of the questions, do I really want a second life? So second life, it's this online world, it's very pervasive. So you can think of, for you programmers out there, if my life.state equals boring or limiting or something else, then what I want to do is I want to get a new life, and then I want to set the state of that life to exciting, and then I want to live. Okay? You guys good? Okay. So if you think about this, maybe people really want to escape. So same code, I just modified it. So again, if my life is currently limiting or boring, I want to save my life. I want to get a new life. I want to set it to exciting. And then I want to live until I'm done. And then I want to get my old life back and live that one. Okay? So you can think about this as escape. Okay? And escape is really important. Escape is about what you do on the weekends. It's about what you do when you're trying to learn something. It's about when you pick up a book and you read it. It sounds really odd, but this successful escape needs support for long-term immersion, for staying in something for a long period of time. It combines all of the senses together, and we need to reduce fatigue in order to do this. So one of the things that we did is current work that we had a poster on last year, and we're submitting. We've done some user studies that we're submitting to the VR conference this year. But uses a tilting chair as an input device, takes advantage of the fans that we have and the floor that we have, uses the Oculus Rift, and uses this interesting German chair called a swapper. And it looks like a big joystick, and it actually is a big joystick. So it actually sways from side to side and front and back and up and down, so you can even click if you want. And we put a tracker on it that allows us to sense the orientation and the tilt of the person. So they're sitting here, they have the fans around them, they have the vibration in the floor, and Rob, show the video now. Anything? Where'd you go? No, okay, we'll do it this way. So this is the... walk. Okay, I'll go back. Rob showed the video. Oh, close. Let's go. Okay. So this is, again, trying to do all these things, non-fatiguing, multisensory. We haven't actually found that the sound makes a difference. We found that the vibration actually helps people to orient a little bit better. Again, we're writing that up now. Another kind of interesting interface that we've come up with has to do with multi-finger gesture, kind of non-fatiguing interaction. The idea here is in virtual reality, there's typically three types of movement you want to be able to do. You want to move with high precision locally, like I want to walk up here. I want to be able to move and adjust something. I also might want to be able to move to the other side of the room, and I also might want to move to the other side of the world. And these are three different types of things. I don't care about precision. If I'm trying to go to Dunedin from here, I don't need precision right now. I just need to efficiently get there. And so there are locomotion techniques that allow you to do this. And what one of my bright PhD students came up with was one interface that allows you to do all three kinds of these things. So this is really, what he does is he takes a pressure sensing trackpad, which are now becoming standard. And if you want to walk, you do this interaction. You basically you make your fingers into your legs. So you can walk slowly, you can take slow steps, you can walk in different directions, basically just doing this. And if you want to go short distance, you can get on a Segway by making this gesture. And now you can make a Segway. You guys know what a Segway is? So you get on a Segway, and now you can make this gesture to move kind of medium distances. And people understand what a Segway is. They know how to turn, they know how to move, and you can move much faster than you would if you did this, right? And if you want to go really far, then you do this gesture, and now you're on a surfboard. So now you can actually fly long distances in 3 dimensions just by controlling yourself. And you can switch between these really easily. You can also, he worked on a horse metaphor now, so you can actually use all 4 fingers and do kind of a medium distance horse thing. So really bright stuff. And this was actually won a poster award at the 3DUI symposium this year. It was a brand new work. So the last thing I want to show you is a PhD student who just graduated. He's working now at Microsoft on the HoloLens project. And the idea here is called hybrid virtual environments. And this, I think, is probably the most important thing. I probably should have led with this. And the idea here is, if you think about interaction in virtual environments, often what you do is you give them a device like a Wiimote, and you let them use it as a pointer to select something, and then they pick it up, they pick the device up, and it's like they have a skewer or something. Or you let them use your hands, and they make a grasping gesture, and then they can pick it up and look at it, and that's about it. If you want them to do anything else, like change its color, there's no kind of standard way to change a color in the real world. This gesture works as a grabbing gesture because that's similar to what we would do in the real world. But anytime you want them to do something abstract, we don't have a way to choose a color in the real world. So you invent stuff. So the idea here is typically what you do is if you've given them a wand to select stuff, you have them use a wand to select a color. Like you bring up color bars and you have them slide, and it's very awkward. So his idea is to make a hybrid interaction. So the idea here is you have a wand of something like a Wiimote, and you can select something. And once you select it, you can then have a tablet mounted on your forearm, and you can do multi-touch gestures here. So for instance, if I want to select a texture to apply to the table, I can go through here and I can select a texture from my texture catalog, and then I can apply it using the wand, right? So now what I've done is I've given them a way to be very effective and efficient here, combined with a way to do this task in an effective and efficient way, right? So we're really good at multi-touch and selecting, and we're really bad at like scrolling through things in space. So you could put everything up here and say, well, you know, you scroll through and then you select one. it's very, very awkward and time consuming. So the idea is to offload it onto things that make more sense. So use a travel interface to help you travel, use a selection tool to allow you to select, and then use something else that makes more sense. So he did a series of studies. Doug Bowman was like the big guy in this field, was on his committee and ripped apart his early drafts and everything else. Is very happy with what came up. The nice thing is, if you're working here, you're not having your hand up all the time. So there are these things about it's non-fatiguing. You can really precisely take your time down here to do stuff, and it's not like you're getting tired. Whereas if you're always up here, you're getting tired, you're getting less precise because all this. So there were like a lot of really big things that came out of this, and I'll show you a video. This is like the second study he did, where again he's seated, the swivel chair is tracked, his head is being tracked. He's got a tablet here, he's got a wand here that's being tracked. I'll show you some video of this one. I think. Where's my video? That's not good. I know we gotta go, so. Come back. Okay, so what you see here is there's a lot of stuff going on. This is the first person view that he has in the headset. This is the tablet. This is captured from the tablet itself. And this is an overhead camera of the whole thing. So this guy's sitting on the chair, he's got the wand, the idea here is to fix this virtual environment, which is broken. There's some houses that are too small, there's some trees that need grass under them, there's a whole bunch of things. And so they have a very standard task, like you see these textures are the wrong size, so he had to go in and change the texture sizes. He has to rescale some things. Rather than have them build a virtual environment, he had them go in and fix a virtual environment. And what the focus is the coordination between these. So now you have two things. You have this tablet and you have the world, and there's different coordination mechanisms to make a unified system, because people are like, it kind of breaks the presence when they have to go from one to the other. And so he's got this synchronization where if I select something in the first person view, it's selected in the tablet view. And this is kind of a God, the tablet gives you a God view. You can see where the first person view is. You can see yourself kind of where you are in the world, and it's all updated. Here he's selecting a texture that he's going to apply. And there are multiple ways to do this to kind of support different types of users. This is incredibly, incredibly important stuff in terms of really moving the usability along and leveraging commodity-based hardware to support virtual reality in a really deep way. Okay? Okay, let me go back. Almost done. I know I'm almost out of time. I haven't taken any questions, but if you have any questions, just So everything I've talked about up to now is really perceptual. It's really the user is sensing something. I'm feeding stuff to the user and through the different senses, but I haven't really gone to the brain very much. So I haven't really gone deeper than really perception. And this is where it kind of gets interesting. So it would be interesting if I can go beyond this and add some sort of anticipation or expectation, or build on your previous experience. So we bring our brains with us into the virtual world, and it's silly for me not to take advantage of those things. So this kind of goes back to why I'm changing my definition. It's not just about allowing the senses to perceive stuff, but it's really about feeding the user the essence of what you want them to get, and allowing the brain to fill in the gaps. Because we're really, really good at filling in things. Like if you're reading a book, right? You fill in all the details. It's very, very powerful. So we can prime the user to expect what we're about to show them, right? So you want to remove all the distractions, and you want to kind of prime them. And you could think about this example, okay? If I say, oh, you're visiting my lab, would you like to come visit my virtual reality lab? Like, very common thing, right? Oh, well, you want to come up to the lab and see what we're doing. If I ask the question this way, hey, in my lab, I'm building the PlayStation 7. Do you want to come visit? It's the same question, right? But people are really excited about this one. And the nice thing is people kind of PlayStation 7 people know, okay, I kind of understand what I'm going to do. And our shared understanding is better because we have this common thing. So if I say VR lab, each of you kind of thinks a little bit differently about what you're going to see. But if I give you an anchor point that draws on something that you already know about, that kind of helps in this way. So we're kind of planting the seed. It reduces the variability. So I'm going to skip these because I have to. So it's not really new. So Disney and other guys do this, right? So when you're waiting in line for whatever ride, they're priming the Spider-Man ride. They're priming you. Everything is about Spider-Man, Spider-Man, Spider-Man. You get on the ride. Your brain is so ready to believe that you're with Spidey because you've been going through this. So this isn't really that deep. But so people get this. We just don't really do it much in virtual reality. So it's really time that you can think about this too. If you're sitting on your couch and you're reading a story and the window's open, it's very different if you're reading a ghost story versus reading the newspaper. Well, sometimes the newspaper is worse than a ghost story. But you get a very different experience because your brain is in a certain place. So I'll kind of leave you with this. The point of view really matters. So if you think about a pessimist will look at this glass and will say it's half empty. And an optimist will look at it and say it's half full. An engineer will look at it and say, well, it's twice as big as it needs to be. And a physicist will say, well, actually, it's completely full. It's just half full with air and half full with water. And an opportunist will just drink the water while everybody else is arguing about it, right? So this is really where I want to be. So this is kind of, let's do this stuff, okay? Let's build it. Let's do rigorous experiments and just kind of get at the meat of the whole thing. So let's see, I'm just going to go. So kind of this deep thought, this is kind of the second to last slide. So achieving all of this is really deeply rooted in human imagination. So the human is really important, and not just the perceptual part of the human, but really engaging deeply. And so we came up a couple years ago, we wrote a paper on this. We call this experiential fidelity. So you think about upping the resolution or upping the frame rate, anything you can up. It's never going to get to the point that the human imagination can fill it in, right? So think about, instead of trying to get closer and closer to realism, what if we pulled back a little bit and just planted the seed about something? So I used, in my talk on Friday, I talked about Alien. Right? Think about the movie Alien, where you don't get to see the bad guy, but you see goop and you hear screams and you see shadows and all this stuff. You're just scared out of your wits because you're filling it all in with your own stuff. Okay, I'm actually gonna leave it there.